Welcome to my channel. Today we'll be looking at linear dependence and independence of vectors. So first we define what we mean by linear dependence and linear independence of vectors, and then look at examples. So I'll give you two definitions for linear dependence and then linear independence, and then use the two definitions to see whether vectors are linearly dependent or independent. So let this be a set of vectors. So that is u1, u2 up to uk. Let it be a set of vectors in Rn where k is greater than 2. K is greater than 2. So when do we say that these vectors here are linearly dependent? We say that these vectors are linearly dependent if one of the vectors can be written as a linear combination of the other vectors. That is my first definition of linear dependence. And we already looked at linear combination of vectors, how to write a vector as a linear combination of other vectors in our previous video. So that means you're already aware of how to write vectors as a linear combination of others. Now, if none of these vectors can be written as a linear combination of the rest, then we say that this set of vectors is linearly independent. That's what I would say. That on the other hand, if no vector in this set can be written as a linear combination of the other vectors, then the set of these vectors is said to be linearly independent. So let's look at the other definition, the second definition of linear dependence and linear independence. So my second definition, let me just erase this first. So again, we have the same set of vectors, u1, u2 up to uk. So when do we say that they're linearly dependent? So we say that these vectors are linearly dependent if we can obtain scalars r1, r2 up to rk. Not all of them 0. Some could be 0 or not 0, all of them not being 0. Such that r1 times u1 plus r2 times u2 plus all the way up to rk times uk would give you 0. So when this happens, then we say that if these scalars exist, and they are not all of them 0, such that r1 times u1 plus r2 times u2 plus all the way up to rk times uk would give you 0. And then we say that these vectors, this set of vectors is linearly dependent. But if supposing the scalars are all 0, if these scalars are all 0, and such that r1 times u1 plus r2 times u2 plus all the way up to rk times uk gives you 0, and all the scalars are 0, then we say that this set of vectors is linearly independent. So those are the two definitions of linear dependence and linear independence. So we want to apply the two definitions in our examples. So the first example is are these vectors u, v, and w linearly independent? These three vectors here, are they linearly independent or are they linearly dependent? So I want first of all to use the second definition. And in our second definition, remember that we want to obtain scalars x, y, w, no, x, y, z, such that x times u plus y times v plus z times w will give us 0. So if these scalars exist, if these scalars x, y, z exist, and supposing they are all not 0, and then we say that the vectors will be linearly dependent. But if they are all 0, then the vectors will be linearly independent. So that's what I just did. Let's just go through it. So I have x times the first vector plus y times the second vector plus z. Yes, so this one is not supposed to be equal. It's supposed to be z times 3, 5, 6 equals 0. So it's supposed to be x times the first vector plus y times the second vector plus z times the third vector equals to 0. So let's just multiply out. X times the first element gives us x, y times the first element gives us 2y, z times the first element gives us 3z, and that equals to 0. And then x times the second element, y times the second element, and then z times the second element gives us 0. X times the third element, that is 3x, plus y times the third element gives us 7y, plus z times the third element gives us 6z, that's 0. So we have this system of linear equations which we reduce to echelon form, and we are already aware of how to reduce systems to echelon form. So reducing to echelon form, I want to have a 0 in this position, a 0 in this position. So I would, the first step I would do, just want to remind you what we do there, is that we would take row 2 minus 2 row 1 to give us our new row 2. Then we'll also take row 3 minus 3 row 1 to give us our new row 3. So let's just see what happened. This one times x times 2 will give us 2x. Subtract from this, you have 0. So you can see I have no element here. And then this times 2 would be 4y. Subtract from this, I have negative y, which you're seeing there. And then this times 2 will give us 6z. From this, it give us negative z, which is seen here. And then 0 times 2, subtract from 0, will give us 0. And then, now let's obtain our new third row. X times 3 will be 3x. Subtract from this will give us 0. So you can see there's a 0 here. There's no element here. And then this 2y times 3 will give us 6y. From this will give us y. And then this times 3 will give us 9z. From this will give us negative 3z. And then 0 times 3 will give us 3. No, will give us 0. Separate from this, like another 0. So I have this. Now the next thing that I want is to have a 0 in this position. So you realize that I will only need to add row 2 to row 3. So row 2 plus row 3 gives me my new row 3. Gives me my new row 3. So the first row remains where it is. The second row remains where it is. And then when I just add this, I have 0 here. You can see it's no element here. Then when I add this negative z plus negative 3z, I would have negative 4z. And that equals to 0. Now, so you can see that we can solve this from the bottom. We can solve this from the bottom. So from this, we see that Since negative 4z equals to 0, then it means that z would be 0. So from here we can see that z equals to 0. From the bottom, we solve going up, So when z is 0, moving to this second question here, putting 0 in place of z, you would obtain that y will also be 0. Y will be 0. Then going up to the first equation again, you will obtain that x is also 0. So we found that the scalars are all 0. The scalars are all 0. X is 0, y is 0, z is 0. So since that has happened, it means that the vectors that we were given are linearly independent. And we've used our second definition of linear dependence and linear independence of vectors. So let's look at another example. So the question is this set, let's just remove this, So the question is the set comprising of 0, 1, 1, 2, 2, -1, -1, -2, 2. Is this set linearly independent or linearly dependent? So again, I want to use our second definition to see whether this set is linearly dependent or not. So that means I want to see whether I can get scalars x, y, z such that this would be true. So that's what I've just done here. X times the first vector plus y times the second vector plus z times the third vector equals to 0. So again, we just multiply the same way we did the first example. So this will be x plus 2y minus z equals to 0. Then this will be 0 plus 2y minus 2z equals to 0. And then lastly, I would have x minus z and then plus 2z equals to 0. So I have this system of linear equations which I try to reduce to echelon form and see what I obtain. So I need a 0 in this position. Luckily, we already have a 0 in that position. So the only thing I want now is to obtain a 0 in this position. So that will be achieved by subtracting row 1 from row 3 to give me my new row 3. So when I do that, the first row remains where it is, the second row remains where it is. So let me just subtract x from x to get 0, and then a 2y from negative y to get negative 3y. And then this negative z subtracted from 2z, I'll get 3z. And then 0 from 0, that is 0. So the next thing I want is to get a 0 in this position, and that I'll have row 2 multiplied by 3 over 2, and then the result is added to row 3, and this will give me my new row 3. This will be my new row 3. So let's just do that. So the first row remains where it is, the second row remains where it is. So let me just multiply this one by 3 over 2. So when I multiply this one by 3 over 2, what I get is 3y. And that 3y added to this, I will have a 0. This one multiplied by 3 over 2, it is negative 2. So when I multiply that, I would get negative 3z. So negative 3z plus that would give me 0. And again, this one by 3 over 2 plus that, I have a 0. So you can see that I have 0 equals to 0 as my last equation. Now, so what does this mean? This means that this system, the system that we had here, has solutions. That is what this last row implies. Since we have 0 equals to 0, it means that this system has solutions, and the solutions are non-zero. And so that means our scalars x, y, z exist, and they are non-zero, and therefore our vectors are linearly dependent. So let's look at another example. So that's how I've said, therefore the given vectors, set of vectors is linearly dependent, because we found that we would obtain scalars which are non-zero. So let's look at this other one. It's the same example that we've done before, but I want to use the first definition because we've been using the second definition. For the two previous examples, we used the second definition. So the question is, this example, I don't know whether it's clear here, but let me just rewrite it here. That is this set is this set 1, 0, 1. Let me remove the b and just write 2, 2, negative 1, and this one as negative 1, negative 2, 2. Is this set linearly dependent? And the question here is that use the first definition. So I want to use the first definition. Remember the first definition, we say that vectors will be linearly dependent if one of the vectors can be written as a linear combination of the other vectors. So I just want to see that is it possible that this vector, the first vector, can be written as a linear combination of these other vectors? Or can this one be written as a linear combination? Of course, if one can be written as a linear combination of the others, then this one can also be written as a linear combination of these other two. Or this one can also be written as a combination of these other two. So it doesn't matter which one you choose. All of them, if they accept, if one accepts, the rest will accept. So that's our first definition that I want to use. So just go to the solution. Go to the solution. That is my question. Yeah, so the solution is here. The solution is here. So I want to see whether this first vector times a scalar A plus the second vector times a scalar B equals the third vector. In other words, want to see whether the first vector, whether this vector here, the third vector, can be written as a linear combination of these other two vectors. And that is our definition of linear combination, that we want to find whether we have scalars AB such that A times the first vector plus B times the second vector gives you the third vector. So when we do that, just multiplying through, we have R plus 2B is equals to -1. And then this one, of course, is 0R plus 2B is equals to -2. And then lastly, we have R plus -B is equals to 2. So we have this system of linear equations, and we can solve. From here, in fact, from this you can see that B becomes -1. So you can use any of this. Let me use this. If B is -1, then we have R plus 1 is equals to 2, which then means that R is 1. So you can see that it's true that this vector can be written as a linear combination of these other two vectors. And therefore, what that means is that the three vectors given to us are linearly dependent. So that is when we use our first definition. So let me see another example. And again, I want to use the first definition. Of course, you already know how to use the second definition. So the question is, use the first definition above to show whether these three vectors are linearly dependent or not. So you know that I want to see whether one of the vectors can be written as a linear combination of the other two. So I've chosen on this, and I want this to be written as a linear combination of these other two. So I want to see whether I can get scalars R and B such that R times this vector plus B times the other vector would give me this vector. So just multiplying out, I would have R plus 4B is equals to -3, and then 3R plus 2B is equals to -1, then -2R plus 3B is equals to 5. So let's solve this. Reduce to echelon form, and so we get. So reducing to echelon form, I want a 0 in this position and a 0 in this other position. So my new row 2 will be obtained by getting the current row 2 minus 3 row 1. And then my new row 3 will be obtained by getting the current row 3 plus 2 row 1. So let's just do that. This one by 3, separate from that I have a 0, and you can see. This one by 3 I have 12B. From this I would have -B, -10B. And then this one by 3 I would have -9. -9 from this would give me +8. And then what about this? Multiply this by 2. I have 2 added to this I have a 0. And then this one times 2 I have 8B. Added to that I have 11B. And then this one by 2 I have -6. Added with this I have -1. So from here you can see that B using this second equation would be -4/5. -4/5. What about using this equation? And again, we will find that B has a different value here. It will be -1/11. So it's not possible that the same B would have two different solutions. So that therefore means that this system has no solution. This system has no solution. That we cannot get scalars A and B such that A times this plus B times this would give us that. So A and B do not exist. In other words, we cannot write any of the vectors given as a linear combination of the other vectors. And what that means is that the vectors given to us are linearly independent. It means that these vectors here are linearly independent. Now, so just a summary, we've been looking at three vectors in R3. What about if there were to be two vectors? Two vectors, it's easy to tell if they're linearly dependent or not, because if one is a scalar multiple of the other, if one is a multiple of the other, then the vectors are linearly dependent, if there are two vectors. But if you cannot write one as a multiple of the other, then they are linearly independent. Now, suppose we are given several vectors, even 3 or 4 or 5, several vectors, and 0 is one of the vectors, then the vectors automatically become linearly dependent. If 0 is one of the vectors, so let me just show you. For example, suppose we are given vector 1, 2, 3 is u, and then you're given v as 0, 0, 0, then you're given w as another vector, let me say 7, 5, 6. Then I would say that these vectors are linearly dependent because 0 is one of the vectors. 0 is one of the vectors, so it will become linearly dependent. Now, one vector will always be linearly independent to itself. It's just linearly independent. Because supposing we want to obtain a scalar, suppose we are given vector w, and we are saying that vector w on its own is linearly independent, because if I can obtain a scalar, given a scalar alpha multiplied by w, and I'm using my second definition of linear dependence, you would see that alpha here would be 0. Alpha here would be 0, so all the scalars will be 0. So the only scalar we have there is alpha, and it's equals to 0. So it means that vector w is linearly independent. Now, dealing with R3, if you're given several vectors, more than 3 vectors, given more than 3 vectors, then those vectors are automatically linearly dependent. There's no need of trying to find out, because supposing I'm given u in R3, I'm given, let me say that u is 1, 2, 3, and I'm also given v as 7, -2, 6, and maybe I'm given w as 7, 2, 8, and I'm given another vector, let me say z, and it's 10, -11, 13. Now these are 4 vectors, and each one of them is in R3, so it means that these vectors, since they are more than 3, they are automatically linearly dependent. They're automatically linearly dependent. So that is how we look at linear dependence and linear independence of vectors. So next time I'll look at how can we also show linear dependence and linear independence of vectors using determinant of data.